Hello everyone, we are Team BioPurge. I'm Rohit.
I'm Arthur.
I'm Brittany.
And I'm Krissa.
So let's talk about our idea. Right now, there is no sustainable way that's efficient and requires little human intervention to get rid of invasive species. In terms of sustainability, we wanted to create a design for our robot that did not deplete natural resources and in turn also use sustainable materials, and also somehow improve the environment around the same areas that invasive species live.
First of all, what is biomimicry? Well, biomimicry, as you should probably know at this point, is the practice of utilizing designs in animals or plants and applying those characteristics in order to solve human problems. So what human problem are we talking about today? Invasive plant species.
Invasive species for generations have been brought to the wrong places by, simply put, ourselves. Humans are the root cause of invasive species, which are now dominant in their new habitats and have no natural species to keep them in check. For this project, we are specifically focusing on this issue.
Species like the purple loosestrife, Japanese knotweed, Japanese barberry, black locust, and other invasive plants overcrowd natural ecosystems while also changing soil chemistry, creating the perfect storm to destroy other species while optimizing growth for themselves. Specifically, species like the loosestrife and barberry crowd out imported native species and raise pH levels, making soil unfit for any other plant to grow.
So let's talk about our idea. Right now, there is no sustainable way that's efficient and requires little human intervention to get rid of invasive species. In terms of sustainability, we wanted to create a design for our robot that did not deplete natural resources and in turn also use sustainable materials, and also somehow improve the environment around the same areas that invasive species live.
So the design needed to be able to remove invasive species by using AI technology and designs implemented in already extant animals, such as a claw or something of the sort with a large amount of strength and an ability to pick up invasive plant species and store them easily. In other words, the design needed to be able to kidnap bad plants. Biomimicry itself aims to imitate nature and biological strategies for optimal form, function, process, and strategy to create solutions to human and man-made challenges. The man-made challenge we're facing is invasive species, and the strategies we're using will be explained now.
We have both a blueprint of the side image of our robot as well as a 3D online model of the full robot. The total height of BioPurge will be 2.5 feet. The width of the entire robot will be 3 feet. The width of the wheels will be 2 feet, and the height of the wheel will be 1 foot. The width of the body portion of BioPurge will be 1.5 feet. Our model focuses on a claw shape that can grab invasive species and a compartment where grabbed species can be stored.
The claw used in the robot will be modeled after that of the coconut crab. The coconut crab is a crustacean found across the Indo-Pacific, from islands off the coast of Africa near Zanzibar to the Gambier Islands in the eastern Pacific Ocean. It has been determined that the coconut crab has the most powerful grip strength of all extant crabs on Earth, which is why we would model the claw after that crab.
In terms of sustainability, the most valuable sustainability compromise we would use is creating the robots out of aluminum and scrap metal. Scrap metal is that which can be welded into new shapes, and aluminum itself is called the green metal because it can be infinitely recycled to continuously create the same product, aluminum.
And last but not least, the bodily portion of the Wally shape would be a compartment for storage of fertilizer. Now, the active ingredient in fertilizer that allows it to help plants grow is ammonized nitrogen. Nitrogen-fixing bacteria in the atmosphere and soil produce an enzyme called nitrogenase, which catalyzes the process of converting nitrogen, N2, into ammonia, NH3.
What we would do in our robot design is use the same nitrogen catalyzing microorganisms, plant them inside the compartment to supplement the nitrogen levels before being created into ammonia, and use the rest of the space to store the invasive plant species after they've been cut to supply the vast amount of nitrogen and ammonium nitrate we would need.
We would use mechanical movement to churn the leaves into a paste and mix it with those microorganisms to create a makeshift fertilizer, all originally created with no artificial fertilizer or other ingredients. In terms of the identification of invasive species, a clear drawback that we faced was how we would identify what is and is not an invasive species. Of course, many plants in the area of the invasive species look similar to the species in aspects other than color and shape.
So how would we identify whether or not the plant that the robot was looking at was invasive or not? Well, a unique idea we had while dissecting the grasshopper was the compound and simple eye dynamic. In essence, the simple eye would be used to detect differences in light, and would be coupled in a single eye with a camera that could be tapped into at any time to view from a human perspective where and how the robot is oriented. The compound eye would allow the robot to be able to sense color and shape, and a pre-uploaded database of invasive species pictures in the area where the robot would be left would allow it to identify the plant and remove it effectively.
BioPurge follows all of nature's 9 laws very clearly. In the first place, it is powered by solar panels, which are placed on the roof of its eyes, allowing it to run on sunlight. Second, it fits form to function and only uses the energy it needs by storing the solar energy it collects and using that to power itself throughout the night. Aluminum and scrap metal fulfill the fourth law because they can be infinitely recycled and never need to be disposed of because they can simply be reused for more purposes when the robots are close to going out of order. The cooperation between the different parts of the robot fulfill the fifth law, and the diversity of places that we will be putting the robots in will fulfill the sixth. Local expertise includes the already modeled robot in the Florida Sea, which will be further explained soon. Finally, our design for trying to limit as much human interaction as possible fulfills the ninth law.
Our selected strategies involved a clear plan and research on previous technologies that have been used to solve similar problems. For example, a tried and true method of solving the problem of invasive lionfish in Florida seas already exists and has a similar design to our design, other than the fact that ours would require much less human intervention because of the fact that our robot would not need to be remotely controlled, but instead would act autonomously using light sensors in its eye area. In terms of practicality and testing, this design, like we have already explained, has already been virtually tested and has been successful in killing off invasive animal species. So it's quite plausible to explain how it would be very successful in killing off invasive plant species, since the invasive plant species would not move at all when being kidnapped.
In conclusion, our BioPurge robot offers a promising solution to the invasive species problem. By leveraging biomimicry, AI technology, and sustainable principles, we aim to lessen the detrimental effects of invasive species while simultaneously improving the overall health of the Earth through the recyclable design as well as the fertilizer compartment. Through innovation and effective decision-making, we can strive to make the world a better place for all living things.